here, okay? Good morning, everybody, and welcome to Astronomy 100. We are in week 5. We are close from our first exam. We have week 6, where we first finished the first.
Okay, we're almost there, right?
The exam is going to be on week 7, okay, which is not next week, the week after. So this is where we're headed right now. We have quite a few materials today to cover, so I'm hoping that you guys will hang around. We have one of the things that we need to do is actually we're going to cover the topics that are covered this week. We're going to, actually, I'm going to pull my other laptop and basically do a, did I sign
But
in?
I did the quiz too. I got 20 out of 20.
Okay, okay, very good. Hold on, let's focus on this thing in here. So I have my laptop actually right now, and I'm going to do a simulation using this laptop. And that simulation will give me an overview of the entire solar system. So hopefully we'll go and scan the entire solar system and see what we have. This is basically units 34 and 35. Units 34 and 35 are going to cover the entire solar system as an introduction, okay? So we're going to cover all of its components and go step by step to seeing what they are. We're also going to cover a little bit of how the solar system came out to be. In a sense, its formation, okay? And the other thing that we're going to talk about is the homework assignment that is part of this week. Before I do that, I know some of you probably have questions about your quiz. So what I'm going to do is I'm going to regrade those quizzes. The reason why I have to do that is because Canvas has this kind of grading that is not really what I want to see. For example, you have a lot of matching questions, and a lot of you get them, many of you get them correct, but some of you get most of them correct. And if you get most of them correct, and if you mess up 1 or 2, Canvas will give you a 0 because it doesn't give partial credits for that one. So I really have to override it myself. Probably there is a way for it to do it, but I will go there and make sure that you get partial credits for those type of assignments. There was also another type of questions that were in there that I think you deserve partial credit for it. For example, it was asking you about the metric system, about some units. For example, for the case of the density, the correct answer in metric system is really kilogram per cubic meter. But there were 2 other choices that are used extensively by scientists, including in astronomy. One of them is a kilogram per liter, not as common, but for sure the gram per cubic centimeter is actually used also. And it's actually metric system units too, but not written in the fundamental units in the metric system. The fundamental units in the metric system are the kilogram, meter, second, and ampere. But the thing with it is the correct answer really should be kilogram per cubic meter if you're asking about the fundamental units. But it also, and you're going to see actually today, the numbers that are reported are actually in grams per cubic centimeter. So if you put a gram per cubic centimeter, you're going to get partial credit. Okay, actually a lot of partial credits in this case, because that's actually the unit that you're going to see more often referred to. Okay, if you use kilogram per liter, also you're going to get partial credit. Okay, so these are some of the things that I have to go through. So item 1 of the discussion. Please, if you have any questions about your grade, do not let it sit. Ask me right away, okay? That you have concern about the way that that assignment was graded, so that they can go through it and regrade it for you or look at it. And we probably are going to have a one-to-one session. So most of the time what I do is, if you're right, and I'm not saying you're not, because a lot of times I make mistakes too. So if you're right, then I would correct it. You look at it and you say, hey, everything is fine. If it's still an issue, please request a meeting on a one-to-one basis where we can go through those things and make sure that you're convinced that the grade is the way it's supposed to be. So that's the item 1 in here. Please focus on your grades and make sure you ask me on a regular basis so that we can hammer those things. This is basically an item of discussion. I really don't want it to be in class with a group of other people discussing your particular grade or your particular assignment. That is not how it's supposed to be, okay? So this is something that we have to get it out of the way. So grades are personal, and ask about them so that we can clarify them. So that's the item 1 of the discussion, okay? you want to. For those who are not attending live the class, of course, you have to put it in your own words, okay? So this is how I put it myself, okay?
Is the best way to reach you through email?
Through the messaging of Canvas. The thing with it is, if you guys try to reach me on weekends, a lot of the times on weekends, I'm not available. I'm actually visiting with friends, and it takes a long time for me to respond. But on weekdays, I usually, most of the time, 99% of the time, I respond right away because I'm in front of the computer or in front of the laptop, so I can respond right away to your messages, okay? So through the messages, and that is the best way, actually, for me to be reached. Try to have scheduled things on Wednesday. Wednesday right now, it seems like it's the best day for me to be available for a lot of these things, or Thursday morning or Friday for that matter, anytime, okay? So the thing with it is, I know I have office hours scheduled for today and yesterday, but those hours are really, I'm sometimes pushing classes, and the classes, they collide with those office hours. And sometimes I have people who have urgent matters to meet with them. And even at times, basically what I do a lot of this videos, try to put the proper editing for their, the captioning, because they're required to do captioning and post them for you guys, for the rest of the class who are not with us in here. And fortunately to say about your class, the vast majority are not here, but 2/3 are not right now live with us. And that's, I mean, the class is supposed to be async anyway, so it's within their rights, okay? So that's what I have to do for them too, and for everybody else also, okay? But the best day is actually anytime on Wednesday, but I have to be basically notified beforehand. And you don't have to stick with the 1 to 2 o'clock on those times when it's supposed to be on Wednesday or Thursday morning, unless we have a planned activity for the entire group or I have something else. Again, you have to notify me ahead of time so that we can meet. And Friday, unless we have a department meeting, which they do also sometimes happen, okay? Or I have, like last Friday, we were actually in a meeting in the morning, but I was available in the afternoon. And even has sometimes Saturday, I scheduled a meeting with one of you guys, actually not from this section, but another section on Saturday in the afternoon. So hey, even in the weekend, if we plan it ahead, it's fine. We can do that too. So this is basically in terms of the first thing. I posted the interpretation of the prompt. This is item 1. So you can put it in your own words, or if you choose to, grades are personal and ask for clarification. Okay, you can put it in your own words. This is not everything. There is another item that is of extreme importance that I really want to also relate it more to the topic than this one up to this week. Okay, so let me get into this week's content. And let me first of all switch to the student view before I share it with you guys. And let me do that as a student in here. Let me share the screen. So this is week 5. Okay. You guys are basically expected now to see more of this, for more or less these forms in here. So we have the week's objectives, which are going to talk about them. The week before review, which are important to connect us back to the concepts from the previous week. We have had a meeting, which kind of an odd meeting on Thursday last week. So I connected that training in here, or that session in here, okay? And then this week's discussion is going to go here, okay? Item 1 is already mentioned, so there will be at least another item in here. So please hang around, do not leave, okay? The 2 units that will be covered, these are basically the interpretation, the short version of them. And then the homework assignment. I'm going to go in detail about this homework assignment, okay? And I will explain the rationale behind it, the reasoning why I'm doing that too, okay? So week 5 objectives are in here, okay? These are the concepts that are covered in this week. So what we're talking about is the solar system this week, okay? This unit 34 and 35 from the book. So we're going to do a little bit of jumping in and out of the book because of the order that we want the class to be delivered. So units 35 and 34 and 35 basically talk about 2 points, 2 items really, okay? The first one is an overview of the solar system. The main thing, of course, is the sun. And then you have the planets that are grouped into two groups. The inner group, inner planets, and the outer planets. There is a big distinction between these two planets in terms of structure, in terms of size also. The inner planets are smaller, the outer planets are larger, both in mass and volume, both in mass and size. The inner planets are denser. The outer planets are less dense, okay? The density, if you take a volume, 1 liter of planet Earth, for example, and compare it to planet Jupiter, the 1 liter of Earth weighs more than 1 liter of planet Jupiter. Okay, that is a fact. This is a property. Why, you ask? Why is that? Well, it has to do with the structure. The Earth, Mars, Venus, and Mercury, they're made out of two main components. They're made essentially of minerals and rocks. Whereas the outer planets, they're made out of two essential ingredients: ice and gas. Water and gas, basically. Water in the form of ice. There is a line between Mars and Jupiter where water freezes automatically and becomes ice. That's why we say ice in this case. Yeah. So in terms of structure, can we turn off the microphone? Okay, good. So there is a line between Mars and Jupiter where water freezes, okay? And that is the distinction between the two. In terms of density, which is this number in here, mass over volume, the Earth is the densest compared to any other planet in the solar system. It's the most dense planet. The least dense planet is Saturn. In terms of density, the outer planets, Uranus and Neptune, are slightly denser than Jupiter and Saturn, but they are less dense than Mars, Venus. Of course, Mercury and Earth are a lot denser. Mercury is slightly less dense than the Earth, that's all, okay? Meaning that they have a lot of, especially with the case of Mercury, there's a lot of minerals in it, okay? But it still has silicate in it. Silicate is rock, okay? So those are the planets. In terms of proximity to the sun, Mercury, Venus, Earth, Mars. The outer planets, Jupiter, Saturn, Uranus, and Neptune. Anything outside of Neptune, on the other side of Neptune, is called a TNO, trans-Neptunian object, okay? For the most part, all of these objects are trans-Neptunian objects, TNOs. The exception is Ceres. Those are dwarf planets. They're smaller than regular planets, but big enough to have a spherical shape, basically. And the biggest one of them in terms of mass and size is actually Eris, followed by Pluto, and the rest of them in here, okay? But these are not all. There are more of them in here, okay? I'm not mentioning every one of them, okay? One of them that is of interest to us is Vesta, actually, which is actually in the same region where Ceres is. Ceres is actually between Mars and Jupiter. And then we have the moons. When it comes to the moons, all the outer planets have moons. There is another structure that all of the other planets also share, and that is rings. They all have rings. The obvious one is of the Saturn, but they're all, including Jupiter, Uranus, and Neptune, they have actually rings too, okay? They have a lot of moons, as I was saying. So this is a common feature. The inner planets do not have moons. Mercury does not have moons. Venus does not have moons. Mars has two captured rocks, which, if you want to call them moons, they're too tiny, too small, okay? Deimos and Phobos. Now, Phobos. There is a, for Earth, that's an exception. That's an odd thing for the Earth to have a moon. Okay, as a matter of fact, it's so odd that that moon is actually big. So the Earth is an exception when it comes to this issue of the moons, okay? Moons are an interesting topic by themselves, okay? The asteroids, we have basically three different distinct, two, possibly three, okay? You have the first one, which is the asteroid belt. That's where Ceres is. And that is between Mars and Jupiter. And that is the asteroid belt. And then you have the Kuiper belt, which is just at the outskirts of Neptune, from the other side of Neptune. That's where all of the other objects are. So the Kuiper belt is actually where the TNOs are, except that sometimes comets can actually come from that region and go all the way closer to the sun and move out. So what the comets are mainly objects that have, again, we talked about the structure. This object, they're made out of mainly ice. So the ice, when they are far away, when it is far away from the sun, it's icy structure. When it gets closer, it warms and vapor starts to evaporate, and that evaporation develops a tail. Where is the tail coming from? It's coming from the radiation coming from the sun. And as that radiation hits the surface, the material now, since it's melted, basically is ejected and forms that tail that is coming from the comet. And it goes around and comes back. When it comes back, it crosses the line of the frost line between Jupiter and Mars. And at that point, it's going to freeze again. It's going to be an icy solid object again. And it's going to go in its motion. So those are comets. Okay. In addition to that, there is another structure far, far, far away, and that structure is the Oort cloud. The Oort cloud is an odd shape. I'm going to talk about the entire shape. Now, the biggest player, of course, in the solar system is the sun. The sun, by far, in terms of mass and in terms of size, it is the main thing. It represents the main components of the solar system. The thing with it is all of this object that I described up to this point, with the exception of the Oort cloud, therefore they're on the same plane, more or less. Okay. So now we need to understand how the solar system formed, and for that we have to come up with a theory, and that is the point 2 of the discussion. So before I get to point 2, let me talk about something else. Let me show you, first of all of these things that I was talking about, including the paths that we described them using Kepler's laws. So I'm going to pull my laptop. Okay. I'm going to stop sharing that screen. And let me find the and let me first of all launch the simulation in here. Stellarium, not Stellarium. It's Universe Sandbox. This is actually a simulation software. This is unlike the Stellarium. Stellarium gives you a real view of things. Okay, it does not really do much other than where the objects are in real time and how they look like based on the best, basically, pictures and the best knowledge that we have. Okay. And even it gives you a realistic view if you use a telescope, for example, a zoom in on an object. So Stellarium is more like the planetarium that we have on campus. This software, the one that I'm launching right now, is actually simulation. You can do a lot of things with it. You can take, for example, the sun and increase its size and see what happened to the planets, or decrease its size and see what happened to its surface temperature, for example, and what happened to the things around it. Or take, for example, planet Earth and move it away or closer. So you can do a lot of these things with it. So it's really an interesting software to have. So let me first of all share the screen. So if you happen to have this software, it's actually a nice software to have. It's called the Universe Sandbox. Basically, all I did is I froze the time on it. So let me put this laptop away a little bit, since I can manage with the screen in here. So here is where the sun is. Okay, it's really the center of everything in the solar system, as you can clearly see. I am far away from the sun at this point. I am at a distance of about 5 astronomical units from the sun. I am as far from it as where Jupiter is. Okay, so let me zoom on it. If I can zoom on it, the mouse is responding to me. Some batteries, okay. Yeah, I guess I am zoomed in on it, okay. So let me get closer to it. I want to cut through it, it's going to be hard to see things inside, okay? Because of the different structure in here. You can't see much of it, but it's mainly gas, really. That's what the sun is, okay? The sun is made up of mainly hydrogen and helium. 75% hydrogen, 25% helium, and traces of other elements, okay? So that's basically what the sun is. The sun is made up of different layers. The three main layers are the core of the sun, where the nuclear reactions are happening, really. And even the core is divided into the inner core and the outer core. The inner core is where the nuclear reactions are happening. The outer core is where basically the helium and all of the stuff that comes out of it, and hydrogen also are there. So the nuclear reactions are happening well inside the center of the sun. And then you have a layer that is between the core and the upper layer, the one that we see, okay? The surface where we see the sun is about 5,000 Kelvin. So if I look at the temperature, it's about 5,752 Kelvin. So that's the surface temperature, not the inside temperature. This temperature is not high enough for nuclear reactions to happen. If you go inside the core, it's in the millions of degrees, but tremendous pressures also because of the sheer volume. From end to end, from this side to this side of the sun is 1.5 million kilometers. It's a big size in here, okay? To give you an idea, the diameter of the Earth is about 12,000 kilometers. So this is many, many times bigger, okay? And in terms of mass, of course, it's millions of times bigger than the Earth. As a matter of fact, you can take 1 million Earths and put them in here to fill the sun in it. So it's a big structure, both in terms of mass and in terms of other properties, okay? So the mass in here, it's in solar masses, but I can see how many Earths there is, and it's going to be very close from 1 million. No, it's actually the volume. I'm sorry. The volume is about 1 million, but the mass is about 300,000. Okay. Where is the radius? Radius is, if I express it in terms of the Earth radii. So this software is actually very nice software to have. Okay. It's about 110 times in radius from here to here. But of course, you have to cube this number. You have to multiply 3 times by itself to find the volume. Hence the word, the number million is actually more than 1 million. Okay. 100 times 100 times 100 is 1 million. Okay. But you have, don't forget, you have the 110 actually. Okay. So this is the properties of the sun. Again, it's made up of nuclear reactions. So what's happening inside the core, the inner core of the sun, is 4 hydrogen nuclei, which are 4 protons really. They combine to make 1 nucleus from helium, for helium. Okay. And in doing so, they produce 2 things. They produce photon, which is light really. And they produce also neutrinos, which are light particles that don't have a charge and don't interact with anything. And they come zooming out of the core of the sun, right through the outer core, the outer core, right through the convection zone, which is a zone, the transition between the inner and the outer, right through the outer layer, all the way to us. And here it takes about 8 minutes for them to reach us. Whereas the photons, the light themselves, they collide with the particles. They're absorbed with the particles inside the inner core, then the outer core, then the convection layer. Finally, they come out of the outer layer so that we can see what we see on a day-to-day. That's what we use for our eyesight. So we use those reactions. So the photon, actually, the light, the particles of light, take about 100,000 years to reach us. So the light that is hitting us right now on the surface of the Earth today took off from the core, or was formed in the core of the sun, about 100,000 years ago, long time ago. The effect is called the Compton effect, really, what causes the photons to bounce on and off. But the neutrinos, no, the neutrinos, they come through. So if something happened to the sun today, we wouldn't know about it in terms of light, of course, until later. But in terms of neutrinos, we will know a lot sooner about it. Okay. Of course, if there is an explosion, we will know in about 8 minutes what happened. We will not know right away, though. Okay. So this is in terms of the sun. It's really the biggest player, and it's really the main component in here. It's fun to do this software actually and try to make it as big as, to see What happened to it when it goes into a red giant stage? We'll talk about this when we talk about the evolution of the planets. Let's find the next object in the solar system, and that is Mercury. Look how far Mercury is. Okay, so now Mercury, it's far away from the sun compared to the size of the sun. So Mercury, if I zoom on it, this is how it looks like. I'm going to put the sun behind me and look at it so that it's lit by the sun. It doesn't look much different than the moon does, because of all of these craters in it. As a matter of fact, if I want to see its properties, let me look at its composition. First of all, look at the density, 5.43. That is a high density. It's the second most dense object in the solar system after the Earth in terms of planets. Okay, and look at the core in here. It's a big core, actually, relatively speaking, because it's made up of a lot of metals inside, and the outer layer actually is characterized by this kind of impact craters, indicating that this has received a lot of bombardments in its form. So whatever happened to it in the early stage happened quickly, so that whenever if it had an atmosphere or something, it lost it immediately. If it had any kind of geology on its surface, if it was active at some point, it happened quickly because of the fact that of these craters. The heavy bombardment happened really after the solar system formed, and that is what we see when we look at the moon. So the same story happened to the moon. But if I look at the surface of Mars, it has craters, but not as many. So Venus must have had some sort of weathering, some sort of rivers, some sort of regeneration of the surface, so that we don't see this phenomenon. For the Earth, it's the same thing because of the geology. The Earth went through a lot of resurfacing stages, so that we hardly see any kind of features like this on the Earth. I mean, there is still that crater in Arizona and a lot of craters around the world that you can find from that period, but not as much, or from later periods, but not as much as, for example, when you look at clearly Mercury in here. Mercury is the closest object to the solar system. Now, if I zoom out and try to find the next one, actually, you can see Mars on the horizon in there, but I need to find where Venus is. Okay, where is Venus? In here. Okay, here is Venus. Venus is the next object in the solar system. So look at its properties in here. One of the things that you can clearly see when it comes to its inner core, the inner core is a lot smaller. As a matter of fact, I was talking about the core of Mercury, which is relatively big compared to the size of a planet. This one actually has less density. It's still more than 5, but not very close. So it's a lot less dense than Earth, for example, but it's very, very close in size to the Earth in terms of gravity, in terms of mass, in terms of physical size. And the only big difference is that it's thick atmosphere. The atmosphere on Venus can reach pressures of about 90 times the pressures on Earth. So Venus is really, really, really super, in terms of the atmosphere, super thick atmosphere on it, which mainly carbon dioxide, plus also sulfuric acid and some other hostile, basically, elements. So I asked what happened to the water that was in there, because there was water. There are studies that show that Venus had water. If I zoom on it, by the way, you're not going to see much features on it, okay? Because of the fact of its atmosphere not allowing you to see anything on it, okay? So you cannot see any features from the inside. So this atmosphere, you ask about the water, when the temperatures basically went too high, the water broke down into its chemical components, which is hydrogen and oxygen. The oxygen recombined with the carbon to form CO2. The hydrogen, because of the high temperature, first of all, it's lighter, so it must have gone all the way to the upper regions of the atmosphere of Venus. And then because of its high temperature, it gained a lot of kinetic energy, and it escaped the pull of gravity, okay? So it reached velocities that are higher than the escape velocity, and it was lost basically to the outside. So this is basically what happened to the water. So it's not something that you can recover. Of course, Earth comes next. A lot of the things that we know about the solar system and the planets and things like that, we took them actually from studying Earth. So let me go back in here and find where Earth is. Trying to zoom out. And because they are in different locations around the sun, so look at the Earth, its core, relatively speaking, but if I zoom in onto it, one of the features that Earth, we came from the dark side, so let's put the sun behind us to see it. You see it has an atmosphere, which is mainly nitrogen, as a matter of fact, just like Titan and a lot of objects that their atmosphere is nitrogen, but it has a living organism on it, namely plants that took that carbon dioxide and broke it into two elements mainly. One of them is oxygen to enrich the atmosphere and give it more oxygen than what it should have. Plus the carbon was formed into different kind of living organisms. So basically that's what's happened to the planet Earth. It's water can exist in all three phases, basically liquid, solid, and gas. And that's why the atmosphere also has water in it. And it's ideal conditions for life in there. We know a lot about its geology, we know a lot about its structure, and we use those to compare it to other planets and basically make deductions. Let me find where Mars is, because Mars now is a subject of intense study and intense exploration, and we're learning a lot from Mars about other objects in the solar system. Where is Mars in here? Here is Mars. So if I zoom in into Mars right now, and turn into the daytime on it, well, we came right on top of Olympus Mount, which is a mountain on the surface of Mars. And this mountain is a huge mountain. As a matter of fact, it's bigger than the mountain of Mount Everest in here. But it's wider, a lot wider. So it's really a fun exploration to look at this mountain here. And it's probably due to some ancient volcanic activity on the planet, okay? Then you have these features on it, which are much, much larger than the Grand Canyon on Earth. Mars is actually an interesting topic that now we're exploring in greater detail with several landers, actually, and including one of them that we sent, InSight, that we sent in 2017, where we study the structure of the planet itself, and we see the different layers. And we actually study marsh quakes on it. And also the last mission that we sent in February of this year was the one that is for Perseverance, and Perseverance had also another component in it called Ingenuity. Ingenuity was able to fly, which is really a drone that flew on top of the surface, which is a big achievement for our technology. And now it opened up a new era of space exploration, because now we can explore planets and moons using this technology, namely drones. Drones require air, so we cannot do it on the moon because moon is airless, okay? But other planets like this one, it is really a possibility, to the point that in 2027, the United States, or NASA at least, is sending a mission there to recover the capsules that Perseverance is leaving behind from the samples of the surface of Mars, so that we can study those samples, go and collect them and bring them back to the Earth. So the plan initially was to have a lander in there, a rover, go and collect those samples and put them in a capsule and send the capsule to the orbiter, and the orbiter will come back to the Earth basically with those samples. But now the mission is going to probably change, and that's what they're thinking about it, is to have, instead of a lander in there, rover, basically, you're going to have a bigger, much bigger, basically, drone that is going to collect those samples and somehow either send them back or bring them back to the orbiter so that they come back to the Earth. The Chinese are actually planning another mission, or at least thinking about another mission that include fixed wing planes, not drones. And fixed planes basically will have a far greater range of flight, because then you can go over hundreds of kilometers of flight and have a big terrain to explore and see exactly the different geological features and the different studies that you would want to explore with the planet. Of course, landing such an object and taking off of such an object is going to be challenged. Most likely it's going to be landing just like a normal lander and flying off like vertically, like they do some of the military planes. There is another mission also to Titan, which is the moon of Saturn, that they're thinking also having some sort of drone technology there, because of the surface of Titan is super cold, but it has a very thick atmosphere. Actually, it's a little thicker than that of the Earth. It's mainly nitrogen. So as a matter of fact, you can do these things in here. you can explore those things. One of the questions that you need to ask and raise immediately, if you want to fly back from Mars, where are you going to get the oxygen from? Because you need the chemical reaction for the boosters to come out. And for that, Perseverance actually is making the oxygen as we speak right now on the surface. So it's basically harvesting the resources of the land. So it's trying to use whatever Mars offers to make oxygen so that the boosters can basically propel the launcher toward the orbiter. So there's all kinds of interesting things that are going on. And this is really what's happening as we speak. So this is a very interesting topic, okay? So this is, again, Mars. We're learning a lot from Mars, okay? Including there is planned manned missions by private companies, or at least that's what they are thinking to do. And now, before I go into Jupiter, look at this object in here. Here is Ceres, which is a spherical object. That's a dwarf planet, as a matter of fact. That is part of the Kuiper Belt. So this is a dwarf planet, the one that I mentioned in the intro. So it exists past Mars. Mars is about 1.5 astronomical units from the Earth. Jupiter is about 5 times from the Sun. So this one must be somewhere in between them. Okay, so as a matter of fact, if I click on it, try to see some of its properties, we don't know it's inside, so probably we think there is oceans underneath. It's actually an interesting object to study. And let's see here, the general properties in here. Its density is less than that of, but it's more than 2, meaning that that's what the problem is. That's what we think there is oceans under its surface. The fact that it has less density, that means it doesn't have as much minerals and as much rock as, for example, Mars or Earth. So the culprit in here is ice. So since there is no ice, there is probably ice on top of it, but the point in here, inside of it, must be an oceans, and that's what we're trying to explore. And if there is oceans, maybe there is a possibility for some sort of an alien life living in these oceans. So this is actually a Ceres, and there is also this tiny object in here, Vesta. Okay, Vesta, has this actually also, it's another dwarf planet, okay? Exists in the same belt. Let me go into the main player in the solar system, which is Jupiter. Jupiter, which is the biggest planet in the solar system by far, okay? So if aliens are outside looking at us, the main thing they're going to see is actually Jupiter outside of the sun, and probably Saturn. That's all they can see, because the others, everything else is tiny, okay? And Jupiter has this gas structure, as I was saying. Its density is slightly more than 1, indicating that it's made out of basically all outside of gases, and mainly hydrogen and helium. So it's really a gas planet, gas giant to be more specific. And it's because of its motion, it has very high, strong winds on its surface. And those winds, they cause all kinds of turbulence. Among them is this big eye that you see in all the pictures for it. It has a lot of moons, about 70 some odd moons. The 4 main moons that we know are, of course, Callisto, Ganymede, Europa, and Io. The thing with it is, with all of its moons, it forms its own solar system. As a matter of fact, if you look at the different moons around Jupiter, you think that it's actually another solar system by itself. Okay, and that can harbor life too on its moons because of the fact that they get a lot of energy from their proximity to Jupiter. So Jupiter, and then of course, if I zoom out, I'm going to find Saturn. Saturn has a similar structure to Jupiter, with the exception that it does not its density is a lot less, and it's mainly made out of the same gases. Its mass is less, and its diameter is less, and basically it has also very strong winds on its surface, and it has similar structure, especially on top of the polar cap. It has this very hexagon shape on its polar cap in there. Okay, so there is all kinds of interesting things. The magnetic fields for both of these 2 planets are tremendously high. 2 has its own system in there, of moons, but one of the main features that you can see everywhere about it is the rings, which is common to all of the 4 outer planets. Okay, let's zoom out, and we're going to talk about the others more, all of these planets in more detail. Let me zoom out and to the point where I find Neptune. So again, here is Uranus, which has this bluish color, and actually Neptune is more blue than Uranus because of its lower temperatures, and both of them gain this color from their high concentration of methane in them. Their densities are slightly higher, okay? And here is a density for it, which is slightly higher than both that of Jupiter and Saturn, but actually it's still a lot less than the inner planets. The other one is actually slightly about the same density as that of Jupiter. Anyway, the point being in here is their structure is similar in shape. They are a lot less massive, a lot less voluminous in terms of volumes than both Jupiter and Saturn, but they're still big, okay? They're very, very massive objects. They also have rings, and they also have moons, and they also have their own, basically, solar systems. Any object past Neptune is called a TNO, trans-Neptunian object. And that includes, among other things, Pluto. Pluto is a dwarf planet. And the main dwarf planet, if you wish, the biggest one in size is actually Earth. Here it is, okay, which is further than Pluto, okay? And of course, you have all kinds of other objects in this region, and one of them is Sedna, which is also another dwarf planet. So all of these are the planets. You have Makemake, and you have actually more than that. You have all kinds of a lot of dwarf planets, okay? And the dwarf planets, they still have spherical shapes, and they have moons. As a matter of fact, Pluto has this odd structure in the sense that it has a big moon. Its moon, Saturn, is very, very big compared to its size, relatively speaking. Of course, still smaller than any other moon in the solar system compared to the other planets. So again, one of the things that you can clearly see for Sedna is very, very eccentric orbit. See how big the orbit for it is? At some points, very close from the sun, and later times, very, very far away from it. And this is, in a nutshell, the structure of the solar system in terms of planets. In this region is the Kuiper belt. That's where all of these objects belong to. And we're going to talk more about this one. If I zoom out, the only thing, of course, that you're going to see is the path of the sun itself. And at this point, it's only the thing that I'm still, the reason why you see Sedna is because I'm zoomed in on Sedna. And at this point, you only see the sun in the solar system in here. So by this distance, we are in the Oort cloud. We are very far away from it. And so this is the structure of the solar system in a nutshell. So let me stop sharing the screen in here. Hopefully you enjoyed the trip with me. So let me stop sharing. Let me close this program because it's really heavy on. I mean, it's really it's computer hot. Okay. So let me go back into where I was earlier to share that screen and talk a little bit about how the solar system formed. Well, the leading theory, and here is the item 2 of the discussion. The word theory in science is not what we use on a common basis. It's not what people say when they talk about theory. When a person tells you I have a theory, what they really mean is, at least in the common language, is that they have an opinion. This is what they think. And most of the time it's just based on some sort of a hunch or guess. No, in science, a theory is a lot more than that. So the item of the discussion is, the second item of the discussion is, a theory in science is not an opinion. It's far more than that. Make sense for the second item?
Yes.
Okay, very good. So theory is not an opinion. It's far more than that. Let me explain what I mean by that, okay? Let's say somebody makes an observation, Kepler, it doesn't matter, Tycho Brahe or whatever, okay? This observation is not usually a single observation, it's actually a lot of observations together and measurements. You go and take the light and you break the light in its components and its spectral lines and see what happened to this spectrum and what happened to this spectrum and compare it to another spectrum. And you spend a lot of nights basically in there by yourself, I mean, isolated and barely basically trying to get things to understand them and see what they make, if they make sense or not. And you go, for example, and you go outside to the night and you look at a single object in the night, compare it to the objects in the background and see its position and draft it on a piece of paper and come back the next night, the same time, you look at the clock and hoping that the weather is cooperating with you, you locate the object and see how far it moved from the previous background. And you do that the next night and the next night for 1 year, for 3 years, for 17 years, and you're analyzing those data and you're copying it, at least in the old days. Nowadays, you have all kinds of very powerful computers that are tracking these objects for you with tremendous, far expensive lenses and very powerful computers. And you're sitting typing all kinds of algorithms on your computer and trying to get these numbers and trying to track that object. And that object is still a painstaking effort trying to get those data and those numbers and those valuable information. You're looking at a binary and trying to analyze it, trying to see its position, trying to see spectral lines, trying to see its kind of any kind of intensity of the beam, not just basically the line itself, to see how intense in terms of brightness it is, and so on and so forth. And you do all of that work. And now you make a guess. It's not any guess. It's not a wild guess. It is an educated guess, a hypothesis, okay? Based on your prior knowledge, based on your prior experience, based on your data. This is what I think is going on, okay? And you test that hypothesis and test it again and test it again. And you see that it's holding ground or failing. If it's failing, you make a new one, okay? If it's holding ground, now you're going to test it. You make predictions based on the model. Now you put a model together. Okay, this is what's the whole structure is. And then based on that, you make predictions. I'm not talking a single person. I'm talking about a collective group of people working on the same subject with different countries, different languages, different things. And they're putting predictions and they go and test those predictions. And sure enough, the predictions hold true. And they confirm the model that you have in there, because this is something that you have never seen before. And yet you made a prediction based on the model. And sure enough, those predictions are tested again and they hold true. And now the collection of all of that observations and those hypotheses and those models and those predictions and everything else, that is what the theory is. So the theory is really collection or a body of knowledge based on all of these experiences. That's what the theory is. So it's not an opinion. It's not what the way people use it on a day-to-day business. So let me explain the model of what we have now based on what we looked at in terms of different points in the sky, and we saw different stages of formation of different planets and different stars actually, and different solar systems, if you wish, out there, stellar systems out there, and we see it at different stages of it. And we see that some of them are in the so-called protostar level, some of them the star went nuclear, some of them are the star is in there, and the model confirms the different layers and so on and so forth. So again, we have a model, we have a theory, and that is based on observation and measurements. And this is how the solar system basically was formed. This is at least the current understanding, unless an experiment in the future basically messes up for it, then we have to come up with a new one. But at this point, this is what we think happened in the solar system. Before 4.5 billion years ago, billions of years ago, there must have been stars in where we are right now. Some of them went supernovae. Why do we say that? Because a supernova is the only event in the solar system that can produce heavy elements. And there are heavy elements on Earth, okay? So that means that the fact that we have iron, for example, in here is an indication that the supernova must have happened in the area where we are. So those supernova, the materials, after they are ejected in different places, they start to come together due to gravity. So gravity took those tiny particles and brought them together because of gravity is an attractive force. So now, basically, clumps of matter start to get together because of gravity. Here is the problem when two masses come closer together. You have mass 1 and mass 2. If mass 2 gets closer to mass 1, in this case, what happened? It loses potential energy and gains kinetic energy. So it moves faster, in other words, just like what happened with the rubber ducky in the bathtub. If you have put it very far away from the sink, it's going to move around, trying to spiral in, okay? As it is far away, it moves slower. As it gets closer, it moves faster and faster. So it gains kinetic energy. This is a similar fashion because it's losing potential energy, gaining kinetic energy. So what happened in here, this mass of all of this dust, basically, that was in this region, starts to move faster and faster, and it moves faster and faster, it starts to flatten. Just like the dough of the pizza, as you spin it, it's going to flatten. So this is exactly what's happening with it. So it flatten, hence all of these objects I showed earlier were in the same plane, more or less. That's the ecliptic plane. That is because of the conservation of the angular momentum, because the angular momentum is a constant value. So is a vector. As a matter of fact, what happened in here is as this material starts to come together, the angular momentum must be conserved. So there is no external agent trying to push this thing around. They are happening on their own, exchanging kinetic energy and potential energy, basically, intermittently. So what happened in this case, the center of all of this is where the sun was forming and growing, getting more, feeding on more materials. As they fall in, more and more, the temperature increases inside. And the pressure also increases inside. Why the pressure increases? Because more materials now are together. They are basically coming together. So they press on one another more and more. So the pressure increases, the temperature increases because the temperature is the kinetic energy, how fast objects are moving. So that's for the sun. But there are other places also in the solar system where the phenomenon starts to happen, like, for example, where Jupiter is. So that too also started to gather more and more materials. And that's where the Earth was and all of the other places in here. So all of this start to form in the same time. I mean, at least different stages. The first one, of course, and where the most materials are in the center. That's where the sun is. But soon after the sun, Jupiter starts to form, and it fed a lot of the materials that existed there. Saturn also started a little later, and the planets actually started to form in different stages because of the materials getting together in every which way. At some point, the temperature was so high in the sun, reached extreme high temperatures, the pressure was so high, and those are the conditions for nuclear reactions. The minute that happened, the minute the sun became nuclear, that explosion ejected all kinds of materials in every which way and pushed all of the tiny objects out of the way. So what happened at that point, the planets were starved of more materials to grow. So they stopped growing for the most part. Had this phenomenon did not happen at that time, what happened in this case is Jupiter could have continued growing and feeding more on oxygen and more on hydrogen and hydrogen and the helium. The main thing is the hydrogen, and then it could have gone also nuclear by itself because Jupiter also under tremendous pressure and tremendous temperatures inside. So it could have actually gone that way, but it did not reach that point because the sun went nuclear and basically pushed most of the materials, the tiny ones, out of the way. So basically only the big ones like the planets and the dwarf planets and actually the asteroids and all of the objects remain because they're too big to be ejected with the solar radiation. So that is basically of how the solar system came out to be. How do we know about these things? Well, first of all, by looking at different points in the sky, and we see similar phenomenon happening. And also we do radiometry in this case to test the age of rocks and the Earth and asteroids and the moon and everywhere else. And one of the methods that we use is that for the potassium decay. The potassium isotope 40 has a 90% chance or 89% chance of going into calcium form and ejecting two things. First of all, the electron and this particle, which is called an antineutrino. The bar on top of it is an antineutrino. So that's one way of doing it, okay? Another process for it is called decay naturally. This is the third force in nature. This is the force of radioactivity, which is called the weak nuclear force. 11% of the times on their own, potassium will capture an electron, transform one of these protons, because it has 19 protons, into a neutron. So now the number of protons drop by 1 from 19 down to 18. And since the proton went into a neutron, the neutrons now will be 22. 22 plus 18 is exactly 40. But that's argon. Argon is actually a noble gas. It doesn't interact with anything in the periodic table if you look at it. Potassium plus electron plus, of course, a neutrino. Neutrinos are just basically almost massless particles that don't have any charge, and hence the word neutrino. It's a little tiny, not charged, with no charges in them. So this is what I described to you was the nebular theory, okay? The process with which the solar system formed. Obviously, the cores that I've been describing earlier, they're made up of dense materials, like especially if you look at the case of the Earth, that's where the nickel and the iron is. They must have gone inside. And the less dense materials like the silicate materials, they're on the surface or the mantle of the Earth. So again, the process that this happens is actually called differentiation. Differentiation is like when you take, for example, you go to the rocks of the river. You have heavy rocks and small rocks, and you take them and you start shaking them. You will see that the big ones will always migrate to the center and the lighter ones migrate to the top. That is the process with which basically this has happened, with which the material is migrated. Again, this is in a nutshell the summary of this chapter. We still have quite a few things to do, and it's very, very important that we do them. And that is the actual problems from the homework assignment, okay? So let me still share that screen with you to show you what I'm talking about. Let me share this screen. So if I go back to where it came from, this is where the homework assignment is. And the homework is this 5 problems, problem 10 through 14. If you have the book, it's page 99 from either edition, it doesn't matter, 5th or 6th. Please do all of these answers correctly and use the proper units, and it has to have
Is it okay if I could do it the right way?
Yes, okay, so this is the problems. If you don't have the book, here they are, okay? Those are the problems. Okay, if I start the assignment right now, it gives me 2 options for submitting my my assignment. I can do it in here, under text entry. But if I do that, I have to really be specific. I'm going to say problem 10 and start answering in there, okay? Remember, it's complete sentences. So if I hit an equation, a math equation, I can do this. I can go to this ellipsis, backward ellipsis, click on them, and one of them is this insert math equation. If I do insert math equation, it gives me this visual thing. So if I need a fraction, I can do, for example, 2, and I can click inside, for example, 3 or something, okay? And I can do the cubic root in here, for example. I have to put 3 in here, and I have, for example, 27. So again, this is one way for me to insert equations. Now look, all of the equations have been entered. So if I need to do equations, that's one way of doing it. You don't have to do it this way. This is just an option. The other option that I strongly recommend is work out your problem, including with your handwriting, if you wish, and take a picture and upload the file, or use Word for that matter. Please do not use Google Drive or Google, I don't know what that is, okay? Or Dropbox or something else, because of the fact that they have to have a personal account to access it, and you too. And that is really not good for your grading purposes and for actually the college, because they want this thing to be centralized in here so that we have access to everything, and you have access to everything in here. So these are the 2 options: file upload or text entry. Okay. Let me talk about these problems now one on one, so that we see how they are done. So I'm going to share with you my notes. And for that, I'm going to bring a pen. I'm going to change the color. And I'm going to talk about this. Did I change the color to black? I don't like this one in here. Okay. Okay. So again, there are problems 12. Are you guys looking at my notes or not?
I can look at your notes, yeah.
Very good. So I just want to make sure. So 10, 11, 12, 13, and 14. Okay, very good. So problem 10. It says series. Remember when I showed you a series earlier, it was between Mars and Jupiter. Let's see if that's true. Remember Mars and Jupiter. Mars sits as 1.52 astronomical units from the sun. So the sun is somewhere in here. This distance is slightly 1.5 times the distance from the Earth. From the Earth to the sun, that is. And Jupiter was actually 5.20 astronomical units. So Jupiter is slightly 5 times further, slightly more than 5 times further from the sun than the Earth is. That's what this means, okay? But Sirius now, we want to find this location. It says that its period P is 4.60 years. Okay, and the question is, what is its semi-major axis A? And that is the A that we need to find for it. That should put it somewhere in here. That's what we expect anyway, at least from the simulation I showed you. And the question is then, where in the solar system that this place it? It should place it between Mars and Jupiter. Let's see in here. And that is the asteroid belt. Let's see in here. We know from Kepler's laws that P squared is equal to A cubed. This is Kepler's law. Kepler third law. They gave us P. P is 4.60 times 4.60. This must be A cubed. The semi-major axis squared. This is the Kepler's third law. If I multiply this two numbers by themselves, this is going to be 21.16, and this is A cubed. Let me tell you something about this number in here. This is what the calculator gave me. I should not really take the calculator. I have really to take the calculator's numbers with a little bit of suspicion, and let me tell you why. I have a 4, I have a 6, I have a 0. 4 is important, 6 is important, and 0 is important because it's after a decimal point. We call this one sig figs. We have a significant figure of 4, we have a significant figure of 6, so we have a significant figure of 0. So I have 3 significant figures in here. Sig figs. We have 3 sig figs. Okay. Also, this one also has the same, actually the same number, has 3 significant figures. This one looks like it has 4. I cannot have more significant figure calculated than what measured. So the maximum I can have is 3. So this is 1, this is 2, and this is 3. But I have to be suspicious of these numbers because of the fact that I have to ask the question, is this number 5 or more? And the answer it is, because it's 6 actually, it's more than 5. Since it's more than, I'm not going to write it because it's not significant, but I'm going to round it up. That means I have to add 1 to this number. So if I add 1 to 1, that is 2. And I don't have to carry any number. So in here, I'm left with 2, 1, 2. So the reason why I'm doing this now is because we really want to understand the significant business. If you did this in math, you're in good shape. If you didn't, this is an introduction to the points in here, okay? Now, if you use the whole number, that's fine too, okay? At least for this purpose in here. So A cubed is 21.6. That means I have to really use a calculator to find A. I cannot do it without a calculator. So it's a cubic root of 21.2. But I can have a guesstimate at it. I can check the numbers. What is 1 times 1 times 1? Is this more or less, that's the choice, than 21.2? That's a question I really need to ask. The answer, of course, 1 times 1 times 1 is 1, and it is less. Okay, so I need to check another number. What is 2 times 2 times 2? Of course, 2 times 2 is 4 times 2 is 8. And 8 is less than 21.2. Now let's check another number. Since it's still less, so we can go on. Let's check 3 times 3 times 3. Well, 3 times 3 times 3 is 27. And that is more than 21.2. So this is actually more. So what I say in this case, the number must be, the cubic root must be more than 2, but less than 3. More than 2 and less than 3. And that puts it somewhere in here. More than 2 is here, because this is 1.5, and less than 3 is somewhere in here. So the correct answer is somewhere in this region. And it is, then I have answered the last part. I know it's between Mars and Jupiter. I know the number is going to be between those two. Since I don't know how to do this one, let me try it with a calculator. So I'm going to share with you a calculator. Share calculator. So you need, for this part in here, you need a calculator that can do the cubic root. The cubic root is the power to 1/3. That's what the cubic root is. Okay. So if you have a calculator that does the cubic root for you, you're in good business. If not, it's the power to 1/3. So I have 21.2 to the power, open parentheses, 1/3. That is what the cubic root is. And the answer is, sure enough, more than 2 because it's 2 point, and less than 3 because it's 2 point. But the calculator is giving me this whole big number, 2.76765500728889. That is nonsense. All I need is 3 significant figures again. I know the 2 is, I know the 7 is, and I know the 6 is. I'm not sure if it's the 6 or I have to round it up. I have to ask the question, is this 7 more than or less than 5? If it is more than 5, and it is, then I have to round it up and make this 6 plus 1, that makes it 7. Anything after this number is irrelevant. Okay, very good. That's a very good point that Christian is mentioning in here. If you have an iPhone, or at least a lot of the apps on the phones, if you turn it around, it becomes scientific and you can do the cubic root. Okay, thank you very much for sharing that. Anyway, so you can round up. As a matter of fact, some phones or some calculators can round for you. You can tell it with what precision it gives you the correct answer. Okay, so so correct answer is 2.77. So let me stop sharing the screen in here and share the notes. Oh man. So A, according to the calculator, is 2.77 astronomical units. 2.77 is actually closer to 3 than 2, but it's between 2 and 3, as we thought it should be. Okay, here it is, somewhere in here. So that is where Ceres is. That answers the question. Okay. So it's one thing we talk about it and we see it in the model and we read about it, but it's another thing to actually do the numbers. The numbers help you tremendously. As I was saying, homework is not an exam. Homework is to help you learn things with numbers and practice. And that's why I'm getting you in here to do this thing. So I'm getting into in the mode of you guys do these things because they can tell you far more about something than anything else. You can actually do the numbers and you see it for yourself. All of the things we did so far is based on numbers. It's not somebody said so or something like that. It's really based on hard evidence. And that's really what I'm trying to say in here. So hopefully you turn in this assignment and you will have the proper credit for it. 11. If I go back into the notes in here, for 11, it says that Sedna has an orbital period.
But how do you spell Seda?
Sedna. S-E-D-N-A. Okay, this is actually a dwarf planet. Okay, Sedna. So Sedna has a semi-major axis A equals to 526 astronomical units. What is its orbital period? So the first question is, what is P? And then compare that to Pluto. Pluto's year is 248 years, 0.1 year years. What that means is 2.5 centuries it goes on Earth before Pluto goes once around the sun. That's a long time. So that means the last time Pluto was in its current position was when the Civil War was happening, 1790s or 1780s or something like that. Okay, so just to give you an idea of how long that is, because it's far away. So we need to find that of Sedna first and then compare it to that of Pluto. Well, I need to use Kepler's third law. It's the same law. It's the same thing that we used up there. Third law of Kepler. They gave me A. I need to find P. So A is 526 but I have to cube that. That means I have to multiply it by itself 3 times. If I take the square root of this number, that's going to tell me how many years that is. This is a normal square root. You can, guys, complete this one. You're going to finish this number. You're going to find a very large number in here compared to 248. And you saw it earlier when I was showing you, said now it was very, very elongated path. So it takes a long time for it to come back toward the Earth. Okay, so you need to finish this. Okay, complete this one. That's your task. You're going to find it in years. So whatever your answer is going to be here is how many years it goes around the sun once. Okay, and then 12 first. This is 11. So we're going to do 12 now. 12. Suppose an asteroid is discovered with an orbit that brings it as close as half an astronomical unit from the sun and as far as 5.5 astronomical units from the sun. What is its semi-major axis and what is its orbital period? Let me describe this situation. So we have the sun. At some point, this object is half an astronomical unit from the sun. So it's an asteroid. So at some point, it's just half an astronomical unit. And remember, Mercury is 0.4. So this is very close from Mercury. And the other times, it's 5.5 times astronomical units from the sun. So this is its closest approach. And its furthest approach, it's about 5.5 astronomical units. This is where Jupiter is, by the way, 5.2. So it's further away from Jupiter and closer from the sun. Very close, almost as close as the Mercury is. So this is the asteroid. We want to find its A. This is where the sun is. This distance is 0.5, and this distance is 5.5. And if I take the center somewhere in here, this distance is A, and this distance is A. So A plus A, which is 2A, must be equal to the 5.5 plus the half, which is 6. I mean, let me write it explicitly. 5.5 plus 0.5 is 6 astronomical units. From here, we can find A to be equal to 6/2, which is 3 astronomical units. This is easy. Okay. From here, they ask us again to find what the period P is. How long does it take for it to do this whole path, this asteroid? Well, P squared is equal to A cubed, and A is 3. So this is 3 times 3 times 3, which is 27. So that means the year, this is the square root of 27. And square root of 27 is more than 5 and less than 6. Actually, very close from 5. So use a calculator. So you need to finish this part too. Finish it. And the answer is going to be in years. So it's going to be 5-point-something years. 5 years and some change, maybe some few months or maybe a few days, actually. Okay. But we just wanted 5-point-something in years. We don't care for it to be in months or days or anything like that. So you can actually do 2 sig figs if you like, because you have 2 sig figs in here. It's going to be 5 points. Okay, so that's 12. 13. 13 requires a little bit of work, and you really need to think about it. 13, it says if a comet orbits the sun and reaches 1 astronomical unit as its closest approach, and its orbital period is 27 years, what is the maximum distance from the sun? Let me explain. They gave us P, which is 27 years. They said, here is the sun, here is the comet. So at some times it's 1 AU, exactly where the orbit of the Earth is. So at some points it's going to be very close from the sun, as close as from the sun as the Earth is. It doesn't mean that it's on the Earth, because the Earth is it goes on a big path. So it could be anywhere on that path. Okay, and some other times it's going to be very far away. So this distance is X and this distance is Y. The sum of these 2 numbers is 2A. Because somewhere in the middle is the center of symmetry, and this is the major axis. The semi-major axis is given by Kepler's third law. Kepler's third law. By the way, if you're going to turn in this assignment, you're going to explain, you're going to put things in complete sentences. You're going to write everything on here, okay? The one that I was saying, if you wish. Okay, so it says that p squared is equal to a cubed. Well, I know what p is. It's 27 years. So 27 squared, which is 27 times 27, must be equal to a cubed. So that means a is the cubic root. A, not a cubed. A is the cubic root of 27 times 27. And this is not the square root, this is the cubic root. Or if you wish, 27 times 27, the whole thing to the power 1/3. If you do it on a calculator, you're going to find 9. And there is a reason why it should be that, okay? 27 is 3 times 3 times 3, and then you're going to multiply it by 3 times 3 times 3. So it's going to be 3 times 3, closer parenthesis, 3 times 3, and another 3 times 3, which is 9 times 9 times 9, and the cubic root of 9 times 9 times 9 is actually 9. So the correct answer is a 9 AU. Please verify this thing. Don't take my word for it. Okay. So we found A to be in line. We need to say that 2A is x plus 1 because this is x. We don't know how far it is when it's at its furthest point, but we know its closest point is 1 AU. So x plus 1 AU is equal to 2 times 9, or 18 AU. And what number should I add to 1 to get to 18? That is 17. So again, x is equal to 17 astronomical units. Please check and verify. Okay, verify. Okay, don't take my word for it. So this is for 13, 14. 14 is a little bit of a different problem. So it says calculate the speed v in kilometers per second, not in astronomical units or years or anything like that. We're getting actually into kilometers per second of a planet, of an asteroid in a circular path orbit at 4 AU by dividing the circumference by the year. Okay, that's what they say we should do. I need to find the circumference of a circle because it's a circular path. So this is a circular path. This distance is 4 AU, and I need to find the circumference. The circumference is equal to 2 pi times the radius, and the radius is 4 AU. This is A, by the way, for 2 pi A. Okay, I need to find P first. I need to use Kepler's third law still. P squared is equal to A cubed. That means P squared is equal to 4 times 4 times 4. And that is 64, actually. So that is actually 64. Please check these things, okay? Don't take my word for it. P is going to be the square root of 64, and I think the square root of 64 is 8 years. Okay, that is the answer for P. Now I need to plug in everything into the velocity. The velocity, V, is equal to 2 pi times 4, of course, astronomical units, divided by P, which is 8 years. 2 times 4 is 8, and 8 cancels the 8, and the answer is pi, or 3.14, astronomical units per year. Well, they don't want us in astronomical per year. They want it in kilometers per second. So I really have to be careful in here and finish it, do this one in kilometers per second. I know when AU is 150 million kilometers. This part of the first quiz that you guys just finished. 1 year is 365 days, and a day is 24 hours, and an hour is 60 minutes, and a minute is 60 seconds. Okay. So this is how many seconds are in a year, actually. So now I have to multiply 3.14 by 150 million kilometers and divide by 365 times 24 times 60 times 60 seconds. Finish this. You're going to find the answer in kilometers per second, as the question is asking. You guys understand this? Okay, if you have any issues with this assignment, please, the first thing you do is talk it over with somebody, or come back and review this calculations, and or send me a message concerning it. Okay. Sounds good. I know we have a few minutes and then we have to stop because the other class is going to start soon. Everybody's good in here?
Sounds good.
Everything's
Okay.
good.
Very good. So I'm going to stop sharing the screen. I'm going to stop recording. I'm sorry. I'm not sharing anything.